We're going to prove Theorem 3 from the textbook. Theorem 3 states that if a sequence of functions f sub n converges to a function capital F uniformly on a set E, and each function f sub n is continuous on E, then the convergent function capital F is continuous on E. We will prove that F is continuous at an arbitrary point P naught belonging to E. In order to do that, there will be a given epsilon greater than 0, and we'll first choose a number capital N so that the norm of F minus F sub n, that norm is the distance between the convergent function capital F and the sequence of functions f sub n. The distance between them, we call the norm on E, is going to be less than epsilon. For any point P in E, we may write that the absolute value of capital F sub P minus capital F of this arbitrary point P naught is going to be equal to this expression. Now what we did was take this expression and expand it into 6 terms. This is actually the leading term, this is the trailing term, and then we put in 2 terms and 2 terms here, which are nothing more than addition and subtraction and addition, subtraction and addition of the same term. It's a mathematical trick to assist us in our proof of our theorem. Now, what we did now, all of this is the absolute value. We're going to take the first 2 terms and put them in their own absolute value symbols, the second 2 terms in their own absolute value symbols, and the third 2 terms in their own absolute value symbols. Now, we take the first term and the last term, and we say that they are less than or equal to twice the norm of f minus f sub n. Since this is the supremum of the greatest distance between this converging function f and the sequence of functions f sub n, since that is the supremum, it is going to be greater than these 2 terms. So by combining these 2 terms into this term, we can say 2 times this, and we can scratch this term and this term, and say that they are less than twice the norm of f minus f sub n. And then we have this term here, which is simply bringing this term down here. Now, we've already stated that this is less than epsilon, so 2 times this is less than 2 epsilon. And now we're going to show that this term, since f sub m is continuous, f sub n is continuous on the set E, we may now choose a delta so that their absolute distance between the 2 is less than epsilon, whenever P belongs to E and P minus P naught is less than delta. Well, we just said, or just stated, that this term, which is this term, is going to be epsilon. So now we can have this term is epsilon. So now we can say that this expression, capital F sub P minus capital F sub P naught, is less than 3 epsilon whenever P belongs to the set E and P minus P naught is less than delta, proving that if F is F is continuous at P naught, proving that F is continuous at P naught, and if F is continuous at P naught, then F is continuous at E. And that proves our Theorem 3.